Hey everyone, and welcome to this explainer brought to you by ClarifyDeCode. Today, we're jumping right into a massive, honestly kind of terrifying architectural headache that plagues almost every growing distributed system. The exact reason why dual writes cause inconsistency and how to fix it. Imagine this highly relatable scenario. You're building an e-commerce system and your customer excitedly clicks the place order button. But behind that simple click, there lies a pretty treacherous world of distributed computing. So, in a perfect world, the app races into action, it saves the order in the database, publishes an event to the message broker, triggers inventory, fires off payment processing, and notifies shipping. Boom. Everything is flawless. But what if, right after the database saves that order, Kafka, your message broker, just goes offline? Suddenly, your database knows the order exists, but the rest of your system? It has absolutely no idea. Your customer's sitting there looking at a happy little order placed screen, but internally, your entire business workflow is completely broken. Okay, let's dive into this roadmap so we can diagnose this catastrophic failure and implement the ultimate fix. We'll be covering 1. The e-commerce illusion, 2. The dual write problem, 3. The Outbox Pattern solution, 4. Handling duplicate deliveries, and finally, 5. Complexity for reliability. Let's start with Section 1, the e-commerce illusion, and the hidden reality. To see what's actually happening behind that incredibly comforting order-placed screen, we've got to peek behind the curtain at the background operations. You see, to make modern microservices actually work, that single click has to trigger two very distinct tasks. First, we have to save the order into our primary database, like SQL Server. Second, we absolutely must publish an order-created event to our message broker, like Kafka. We have to do this so that all those downstream services, inventory, payment, shipping, know they need to wake up and do their jobs. Which brings us to Section 2, the dual write problem, a really dangerous failure window. This failure window exists purely because our database and our message broker are two completely different independent systems. There's no magical atomic transaction spanning across both of them by default. So to understand exactly why this dual write guarantees inconsistency when things break down, let's look at the disastrous outcomes. In scenario 1, the database succeeds but Kafka fails. The result? You literally have a ghost order sitting in your database that never gets fulfilled because shipping and inventory were never even notified. But scenario 2, that is even worse. Kafka succeeds in publishing the event, but the database transaction rolls back. Now your system goes ahead and reserves inventory, charges the customer's credit card, and preps a shipping label for an order that doesn't actually exist in your database. No way you want to explain that to a customer. So the absolutely crucial takeaway here is this. A dual write means writing to two independent systems separately. If either one fails, your system becomes inconsistent. Now, it's totally natural to be wondering, hey, can't we just wrap both of these in one giant distributed transaction? And historically, yeah, you could, using something called a two-phase commit. But modern cloud-native systems intentionally avoid two-phase commits because they are incredibly slow, they block resources, they're painfully difficult to scale, and they introduce a massive single point of failure. We desperately need a better way. Enter Section 3, the Outbox Pattern solution, embracing eventual consistency. Now, what's really interesting about this is that it's exactly how giants like Amazon, Uber, and Netflix escape the inconsistency trap. The big idea here is surprisingly simple. We don't try to force the database and Kafka to play nice in a single transaction. Instead, we remove Kafka from the transaction completely. We just flat out stop attempting to write to both systems simultaneously. We pull this off by introducing a brand new table directly inside our existing database called the Outbox. Let's walk through this new flow. It's pretty brilliant. We begin a transaction in SQL Server. We insert the new order. Then, and here's the magic, in that exact same transaction, we insert an Outbox event representing the order-created message. Then we hit commit. Because both of these inserts happen in a single local database transaction, we guarantee ACID properties. Either both inserts succeed perfectly, or they both roll back. The whole dual write problem? Instantly eliminated. Okay, but you're probably thinking, how does the message actually get to Kafka then? Well, we use a background worker. This worker just continuously polls the Outbox table looking for events marked as pending. When it finds one, it reads it, publishes it to Kafka, waits for the acknowledgement, and then simply marks the row as published. And if Kafka happens to be down, no sweat, the row just stays pending. The background worker will safely retry using exponential backoff. So it waits 1 second, then 2, then 4, then 8, and it usually adds a little bit of jitter. This ensures we don't accidentally cause a massive retry storm and crash our own systems when Kafka finally comes back online. Moving on to Section 4, handling duplicate deliveries. Because yeah, we have a new challenge. So we fixed the dual write issue, right? But what happens if our background worker successfully publishes the event to Kafka, Kafka acknowledges it, but our application crashes a microsecond before it can actually update the Outbox row from pending to published? Well, when the app restarts, it looks at the Outbox table, sees that the event is still marked as pending, and naturally assumes, oh, I need to publish this. So it sends it to Kafka a second time. The result? We now have two identical order-created events just sitting there in our message broker. Because of this little quirk, we say the Outbox pattern provides at least once delivery. Not exactly once, at least once. To handle this, we absolutely must embrace idempotency on the receiving end. Idempotency is a fancy word, but it simply means that processing the exact same event multiple times produces the exact same result. For instance, the inventory service can use what's called an inbox pattern. It essentially keeps a record of every event ID it has already processed. When a new event arrives, it checks the inbox. If that unique event ID is already sitting in there, it just ignores it. It knows it's a duplicate. By doing this, we guarantee we don't accidentally reserve stock or charge the poor customer twice, even if our Outbox pattern sends the message a dozen times. Which brings us to our final point, Section 5, complexity for reliability, the architectural trade-off. And this brilliantly illustrates what we're really doing here. Let's be totally honest. We are clearly trading the pure simplicity of a direct publish for a much more complex architecture. But when we look at our choices for messaging guarantees, we see why this is absolutely necessary. At most once is fast, sure, but you will lose messages. Exactly once sounds perfect on paper, but it is extremely difficult, super expensive, and highly complex in distributed systems. That's exactly why enterprise architectures almost universally choose the middle ground, at least once delivery paired with idempotent consumers. It's the sweet spot. You get rock-solid reliability without the crippling bottlenecks of those old distributed transactions. Now, if you're going to put this into production, there are a few best practices you need to follow to keep things running safely in the real world. Let's rapid fire through them. First, keep your events immutable. Literally never change an event once it's created. Second, use globally unique event IDs, like UUIDs, so your Outbox pattern actually works. Third, include a correlation ID and a trace ID for observability. You absolutely need to be able to track a request across a dozen microservices. Fourth, always version your event contracts. Fifth, batch publish your events for higher throughput. And finally, set up strict alerting on growing pending event counts. If your Outbox is growing, it means your publisher is failing and your system is lagging behind. So as we wrap up this explainer, I really want you to reflect on your own application architecture. Are you currently doing dual writes? Are you risking silent data inconsistencies every single time a customer clicks a button? Understanding how to balance these complex trade-offs is exactly how we build better, more resilient software. We really hope ClarifyDeCode has helped bring some clarity to this complex design today. I'm going to leave you with this final provocative thought. If your system crashed right this very second, are you 100% sure you wouldn't lose a single customer's action? Think about it. Thanks so much for joining me, and keep building reliable systems.